You've designed and built a new radar, now it's time to test it. I'd like to show you an example of NI's solution for radar system-level validation with this radar target generator, built on the modular PXI platform with RF transceivers and customizable FPGA coprocessors. There are two parts to this demonstration. To play the role of our new radar under test, we're using this 5831 vector signal transceiver on the left. It provides phase-coherent RF generation and acquisition at frequencies up to 44 gigahertz with 1 gigahertz of instantaneous bandwidth. We're using software on the host controller to generate pulsed radar waveforms for the VST to transmit, then analyzing returned echoes to perform the radar processing to detect targets. This user interface on the left controls that emulated radar. We currently have it configured to operate at X-band with a carrier frequency of 10 gigahertz using the pulse width and pulse repetition interval shown here on the diagram. Over on the radar tab, the radar plots its targets that it detects on this rotating PPI display, and each target is annotated with its measured Doppler shift. Below that, we have a plot that shows the individual scan lines as they're received to visualize the returned pulses over time. Those returned pulses are coming from the star of our show, the radar target generator on the left, which provides a closed-loop simulation of the environment and targets for our radar under test. Our target generator is also using a 5831 vector signal transceiver as its RF front end. It digitizes the RF signals coming from the radar over this cable, and then continuously streams that full IQ spectral data over a low latency link to this FPGA coprocessor. This FlexRio 7915 gives us a huge Kintex ultrascale FPGA to use for real-time signal processing. We're using its onboard memory as a circular buffer to digitally delay the signal to simulate the target's range, and then applying other effects to that signal like attenuation and Doppler shift. After we're done signal processing on the FPGA, the resulting digital IQ samples are streamed back to the vector signal transceiver to generate the RF return signal for our radar under test. The user interface on the right side of the screen controls the target generator, which can simulate up to 4 targets with individually configured range, velocity, and RCS models. We currently have 3 targets positioned at different ranges along the same azimuth, and the 4th target is down below on a different azimuth. Those 4 targets are all configured to use a constant RCS, which scales the returned signal power based on the maximum gain setting, which is configured differently for each of these targets. We've also configured different Doppler shifts for each target. In addition to a constant gain, we can also select swirling models for the RCS. Let's select swirling 3 for object 2. And now the return signal power for the middle of those 3 targets will fluctuate over time. We can see that on the PPI display as its dot changes color from scan to scan, indicating different signal powers. Our targets are currently all stationary, but if we want them to move, we can select one of several moving profiles. I'll select moving 1 for object 3, and that will send it traveling around on a circular path around the area. Finally, we can also configure one of our targets to generate clutter, which will move the target around to produce a field of randomly spaced returns. Notice that our first object is in the middle of that clutter field, but it can still be distinguished from the clutter because it has a higher power and a Doppler shift, whereas the clutter returns are not frequency shifted. Keep in mind, those are just the effects we're applying in this example system, but it's not a lockdown set of functionality. The FlexRio is a user-programmable FPGA, giving you the flexibility to implement the specific signal processing techniques you need to test your radar. You also own the IP you create, so you have the freedom to modify it as your requirements evolve. If you don't want to implement those custom features yourself, you can work with NI and our family of partners who have a history of successfully developing tailored solutions to meet different radar test requirements. Now, for this demonstration, we had the radar target generator directly connected to our emulated radar over these cables. However, this target generator could also be used for radiated over-the-air test. In fact, we've taken this very system to an open-air range, connected it to antennas, and used it to generate targets for an actual radar system. The modular nature of the PXI platform also makes it scalable to meet growing test requirements. Need more RF channels? You can add more transceiver modules and synchronize them for MIMO operation. Need more FPGA resources? We have a range of FlexRio and other FPGA coprocessors to meet those needs. You can even mix in other types of instrumentation. For example, let's say in addition to validating your radar system's RF performance, you also want to interface with it at a subsystem level to test the radar processor. There are high-speed digital interface modules to do that. The flexibility of the PXI platform enables multi-level system validation that can scale to meet your needs. To learn more about NI solutions for radar design and test, visit ni.com.